like to start what I would have liked to discuss last time, but let's take the time to do it here. Okay, so here we're actually essentially making some statements here that we have a fairly good comprehension of everything static as far as isolated charges are concerned. However, the stuff around us takes the form of, pieces of junk that have certain densities, certain properties, including physical properties, but also electric properties. And it's obvious that most of this matter reacts to the presence of electrostatic fields in a certain way. And we would like to try to characterize this. So talking about the effects of an electrostatic field on matter, we have to talk about the notion of polarizability. Okay, and what does that mean? We know that this kind of idealization from a couple of hundred years ago, that we have continuous charge distributions with neutrality and whatnot, this is not correct. We know from quantum mechanics that there's a very big discrete nature to atoms, to matter. There's a very rapidly varying density of positive and negative charges as you swim microscopically between your atoms and molecules. Okay? And the notion of something smooth is just because you're taking an average from a certain distance of all these little pieces that exist. So if you look at the pieces themselves from a certain distance, they will essentially behave like something which is neutral, typically. If it's not neutral, it will try to become neutral again to minimize the energy. But if you look at an atom from a certain distance, it really looks absolutely neutral. But if you were to shine an electric field onto this atom, because the electrons and the protons are, spatially very differently configured, then the protons and the electrons will respond differently to the presence of this electric field. So if you have no field, then the average, the spatial position of the average of the negative charge distribution coincides with the spatial average of the positive charge distribution. Okay? However, if you were to put an electric field around your atom, the electrons would move one way and the protons would move the other way. Therefore, there would be a kind of tearing apart of these two different distributions. That means that really there is a certain dipole moment that can be induced by the presence of an external electric field like this. Okay? And that is the notion of polarizability. So in the very simplest case, what occurs is that you can think of this piece of matter or this atom in the presence of a field as developing a dipole moment. And this dipole moment goes along the field direction in the very simplest cases, because you would imagine you shine it in a certain way and then the atom just orients itself to have the dipole going that way, so it really fully minimizes its energy. It can get much more complicated than that, and we'll talk about that just a tiny bit. Okay. Now, when you think of that little dipole, then the forces that are acting on it are quite straightforward. Let's say that you put your origin at the position of your negative charge, then there's obviously a torque acting on this dipole coming just from the Coulomb interaction, or just from the interaction with the field, and this torque will tend to rotate the dipole in the direction of the field. Okay, so P is my my little polarization that I have here, and if I have an electric field which is not parallel to that dipole, then the dipole will try to make itself parallel to it. Okay, and then so this kind of torque is really just doing the moment of force from, say, putting your origin on this one here. So that's the simplest thing. So this polarization. So essentially, it's the induced dipole moment on your little atom. Okay, so that's the simplest thing. So these dipoles, they just have a torque when they're in a field like this. Maybe just quoting again, we'll not use that very often, I think. There is, besides the torque, there can also be a kind of drift of a drift force in here if the field is not uniform in space. So if the field is increasing in a certain direction, then the dipole will have a tendency to try to go in this direction as well to minimize its energy. Okay, so if you just again write down the forces on these two charges separated by a certain distance d and with a kind of charge differential d, the product of d of the distance and the q being this this dipole moment here, you'll see that you can just from the Coulomb law write this this expression for the force. Okay, but again, it's just like not super crucial. So so that's the idea. The energy of this is just starting from a certain zero. Just checking whether your dipole is aligned with the field or not. If it's not aligned, it will try to align itself to the field in order to minimize this this product here. Okay, so that's just like basic physics of simple dipoles. These are isolated dipoles again, so just like almost single particles. Now, the point is that we are interested in bulk matter. We want to look at chunks of material that are composed of macroscopically large numbers of atoms. However, we don't lose the microscopic picture completely because these chunks of matter are composed of atoms that are polarizable. Therefore, in my chunk of matter, I could look at little sub chunks here, microscopic sub chunks composed of many, many atoms, however, showing a certain average dipole moment per unit volume. And this dipole moment per unit volume is an object which is called the polarization, big, vector big P. Okay, so that's this big P is just the dipole moment summed up in a little chunk per unit volume. Okay, and of course the polarization itself depends on the external circumstances. If you don't have any external field, maybe this is zero. If you do have an external field, then if you make the field stronger, this polarization will become stronger. Okay, but that's what we'll try to use to characterize these objects here. Okay, yeah.
The dipole moment and the magnetic.
Yeah, so be careful here because we are back on the electrical side of things. So these are electrical dipoles. These are not the magnetic dipoles that we will do next time. So this bit about the vector potential and the multipole expansion was just to close off last time. So we are back in electrostatics here. So if I say dipole, I mean electric dipole. Two charges split by a certain distance. Okay, so magnetism we'll do back later. Okay. Have you seen polarization before in your first class? I think typically they would mention it in passing like this, but we'll try to formalize it again a little bit more. Okay. So is that cool? You kind of visualize this this chunk of matter, maybe a piece of rubber or a piece of wood or whatever, and you put it in a field and it reacts to it by redistributing its charges. And the way you will characterize that is by looking everywhere in that piece of matter. What is the density per unit volume of these electric dipole moments that you have? Question. Absolutely, yeah. So we'll talk a little bit more about the kinds of types of objects you can have. So if you have a conductor, then this is a piece of matter which is infinitely polarizable because you put a tiny field in there, and woof, charge goes as far away as it can. So it has the highest possible dipole moment that you can have. So here we're thinking about chunks of matter that don't have free charge flowing left, right, and center. It's more that the charges are kind of stuck in place. All charges are like linked to each other with these springs, and you can pull on them to deform the whole thing, but you're not actually pulling them apart and having them move freely. Okay, so we're kind of introducing a new class of materials away from conductors. Conductors are a limit of this. When we talk about the parameters here, they're just a limiting case of these things. Okay. Question? I'm sorry?
What was the formula for the electric?
Of what? Of the yeah, so we maybe this is the answer to your question, because what we had done before was the expression for the potential and for the field of an isolated dipole. Okay, and this is the one that I've got like conveniently here. So if I've got one dipole like this, and here just so we had done these cases for these isolated dipoles, and now what we're going to do is really just invoke the principle of superposition to write down what these things are. Okay, so we had started from the potential for a single dipole, and here, so be careful, I don't have hats here, so then I have to put this in cubes. So what was the electric potential of a dipole? I had a certain plus minus configuration that gave me a dipole, electric dipole going a certain way, and then the field that I had fell like 1 over r squared. Sorry, the potential fell like 1 over r squared away from this. So the actual force would fall like 1 over r cubed. Okay, and it depended also on the direction that I was away from the dipole. Right, so you remember the field of the dipole had these arrows coming out and then coming back in at the bottom. And not for an isolated dipole. Okay. But now what we have really is, by superposition, we can use this formula for an isolated dipole and just say that we sum it over all the places where I have a non-zero polarization. So here I've got my chunk of material. My chunk of material has all these little places with a certain dipole moment per unit volume. And I'm now computing the potential somewhere as the linear superposition of the dipole terms coming from all these little chunks forming my material. Okay. So you might say, what about the quadrupole moment, etc., etc. This is only the dipole moment. Okay, but it's still the leading one that you have here. So the object itself, the chunk of matter that I have, has a certain shape, and inside that three-dimensional shape, this is like three-dimensional, so just imagine a big chunk. Inside that three-dimensional shape, I've got the polarization vector, which is a local thing to each and every little cube I can think of in here. And if I'm measuring the potential at a certain place here, it's just the dipole term coming from that little chunk summed over all the chunks inside my piece of matter. Okay? So that's the idea. So in a sense here, we're not doing anything very special. We are curtailing the shape of our potential to a dipole term. We are invoking superposition to just say that I sum over all these things here. But there is one